Surprised it didn't. Oh, it told you it was recording?
Yeah, yeah.
Okay, good. And then this one's
I
host,
just
so it didn't tell that one.
sound.
Excellent. Okay, great. So let me just do a quick intro. So we are here for computer science seminar today. We are happy to have our own Adam Poliak giving this seminar. He is a Roman family faculty fellow here at Barnard in computer science. He came to us from Johns Hopkins University, where he got his PhD and was a member of the Center for Language and Speech Processing. And he has also had research positions at MIT Lincoln Laboratory, Bloomberg LLP, the Human Language Technology Center of Excellence, and has been working here, running a research group focused on natural language processing, some of whose members are here today. And he his research has been funded by the FDA, Google, Columbia School of Nursing, DARPA, and others. And he's going to talk to us today about his work on the limits and applications of natural language processing. And before I turn over, this is grab and go fruit, no eating in this room, but please feel free to take some on your way out.
Thank you. Thank you, Rebecca. Thank you, everyone joining in person and on Zoom. It's my first time doing a lecture with my mask on, so if I'm too soft, let me know. And if you have any questions, feel free to interact. So I want to just sort of level the playing field, make sure we're all sort of on the same page. What do we mean by natural language processing? Have any of you, all of you heard this term before? Anyone not heard this term? No, so natural language processing, basically lots of views of it, but we're going to start out with this view that it's a subfield of AI that's really focused on building human language technology that we can interact with, right? So we have things like Amazon Echo, which we use every day for music for my baby. Siri, a little more frustrating, but we've used things like Google Translate. I'm sure most of you have used Grammarly for your essays, things like that. So here really are great examples of successes of natural language processing, where we've moved from the research lab to real production, real products, real use cases. However, when they fail, there can be some big issues. So here's an example from about almost 2 years ago. It's okay showing an example from January 2020 because the past 2 years have been a big blur. So how many of you have heard of this example before? Yeah, so here what happened basically, Xi Jinping, the premier leader of China, was visiting Myanmar or Burma, and Facebook automatically translated his name and blurred it out right here, because everyone guesses what that is, right? So you can see here when they fail, they can make big errors and big issues, right? So here this caused a whole diplomatic brouhaha that should be avoided. So really the question of why do we want to explore the limits of NLP models, right? So if we want to improve our system's ability to translate, we should understand where they fail. So if we want to understand our system's ability to summarize, we should understand where they fail. If we want to improve our abilities, our NLP system's abilities to spell check, like Grammarly, like the paperclip on Microsoft Word, and those in the 90s and before, right? We should understand where they fail. And to improve our system's ability to do anything, right, we really should understand where they fail. So the first part, really the majority of this talk, we're going to focus on understanding the limits of natural language processing systems. And we're going to start with this NLP task called natural language inference. And what it is a sentence pair classification problem where we're given the first sentence, often referred to as the premise. Here would be Millie ran across the field. And we're given a second sentence that's supposed to describe a similar scenario, right? So here the hypothesis would be the mascot moved. I hope you all know who Millie is, right? And the goal here is we're going to formulate this as a binary classification problem. So we're going to say, if the first sentence is true, let's assume the first one is true, how likely is it that the second sentence is true? This is inspired by entailment, a phenomena in linguistics, but in truth, although we refer this as entailed or not entailed, this isn't a strict logical entailment, but some sort of fuzzy notion, right? And one thing to note is there are multiple labeling schemas people use. People use, instead of binary, people use three-way classification. I have work from about a year ago where we argued that maybe it shouldn't be a categorical problem at all, rather a regression. But all of that, let's put that aside for now. And let's just focus on this binary sentence, this binary classification problem, right? So what do we think this would be? Given the first sentence of Millie ran across the field, what do we think in the hypothesis the mascot moved? Do we think that would be entailed or not entailed by this example? Yeah, I see one thumbs up. Did I see any thumbs up or down on the Zoom? There are a few people there. No, but I think I saw a few up here. Exactly. So this would be entailed, right? And why is this the case, right? Because if Millie is the mascot, right? And if she ran across the field, that means she moved. Right? So that is really natural language inference. And the goal of natural language inference really has been used as a way to test our system's ability to understand language. So I just want to briefly look at the typical natural language inference modeling approach. So here what we have is we basically represent our two sentences, throw them into some model, get a representation, combine those and make a prediction, right? So if we look back at our example, we pass that to our model view, right? What we do is we encode our context, our premise, encode our hypothesis, and want to make this correct prediction. And there are multiple parts of this modeling approach, but here we're going to focus on just one of them, which are called word embeddings. And the question here that I want to pose to you basically is, how should we represent these words in a way that a computer understands, right? Because we can understand this is a word, we understand what that means, but computers don't speak English, right? Computers speak numbers. So does anyone have any ideas how we can how should we represent these words in a way that a computer would understand? Let's just think what's maybe the most simple approach that I've learned in a data structures class. Any ideas? No? You should give any ideas?
Pointing out. Just like translate it to binary.
Yeah, so maybe we can come up with a lookup table, right? So remember, we've all seen the hashes or lookup tables in data structures and some of our earlier computer science classes, right? And what this basically is let's just have a unique representation for each word. And we're going to call this a one-hot vector, because all we're going to do is each of our words is going to be represented by a vector that's n elements long, and all of the values will be 0, except for one of the values in our vector will just be 1, and that will indicate which word. Right? So here, for example, we can see then how we would represent the sentence or each word, right? So Millie would be everything is 0, except for because this column is 1, that indicates that this word refers to Millie, so on and so forth. Right? Does that make sense to everyone? Yeah. So that we can do basically, right? We can just convert what we had before into a series of these values of 0 and 1s. Does anyone have any issues with that? Why might we not like this? Not like about this.
Can be too complex for long text.
Right, so you're saying can be too complex. So maybe if we have a large vocabulary, these numbers are just going to be, the length of these vectors will be enormous, the size of our vocabulary, right? That's one issue, exactly. Any other issues with that? So we're going to have long vectors, right? Are they going to convey much meaning or not? No, right? Most of these are going to be 0s. They're not going to be 1s, right? Any other issues you might not like with this? Let's really go back to here. Another issue is that these words convey some sort of meaning, right? When we just use these one-hot vectors, there's no meaning between these words. There's no relationship really between these that are apparent, right? So I want to ask another question. Let's take a little side step. How do you figure out the meaning of a new word? Right? You're all at Barnard. You all should do very well on your SATs, ACTs. I know you're great readers, you read a lot. How do you figure out the meaning of a new word?
Decompose it to its elements.
Right, so one way is you can break it up into subcomponents, that's true, but how else maybe, yeah?
Using the context of the word is pretty good.
Exactly, using the context, right? That is something that often the way that we learn new words. So here, let's look at this example. Does anyone know what this word tisguino is? Anyone seen it before? No? Cool, so let's look at this sentence, right? So we have a bottle of tisguinos on the table. Everyone likes tisguino. Sorry if I'm mispronouncing it. Tisguino makes you drunk. We make tisguino out of corn, right? What do we think this is? Some sort of beverage, yeah, that's definitely a beverage. What type of beverage? The soft drink? Probably not, right? An alcoholic drink, right? Exactly. So this is some sort of alcoholic drink. You've never seen this word before, right? But you've looked at this context and you can understand, hey, this is some sort of alcohol, right? And this is, I think it's a Mexican corn beer. I don't remember. I don't have my notes up, but I think let's go with that, right? And this is exactly what tisguino is. And there's this idea in linguistics called the distributional hypothesis, right? Where it says words with similar contexts shared similar meanings. And there's a famous quote from 1957, you shall know a word by the company it keeps, right? And we're going to use that idea basically to learn these vectors or these mathematical representations that a computer can understand, right? So let's look at the word hash, right? Hash can mean lots of things, right? It could mean like potato tots with all hash. It could mean, right, hashing a message in computer science and math. It could also mean weed, right? So here oftentimes we'll need to know the context. Right? So let's look at this example. Right, so I said, about to get my hands on some top shelf hash. I have no idea what the hash price is in my area. There's no one that sells hash in my area, actually. What do we think this is referring to? Weed, exactly, marijuana, right? This is actually an example when I was working at Lincoln Labs on some dark web data. We're doing a lot of like illicit drug identification and things like that. But so what we're going to use is maybe what we call a co-occurrence matrix. Okay, so what we're going to do basically is we're going to have a window size of 2, and we're going to, oh, these circles aren't supposed to be there, but that's okay. What we are going to have here is basically we're going to continue with that matrix that we had before. It'll be, the size will be our entire vocabulary, right? We'll have that many rows and that many columns. And what the numbers are going to represent now, instead of just ones and zeros, we're going to represent some counts of how many times did these two words appear together, right? So if we look at the Mayan area over here, does anyone have any idea why this is 2? Why would this be 2? Let's look at the example.
2 times that we have my area.
Exactly, right here, exactly. So that's why there would be 2, right? And you also notice that this should be a symmetrical matrix, right? 2 and 2. Cool, let's look at another example. Oh, supposed to have those on first. That's all right. So hands on, here we would have 1, right? So that's basically this idea. But let's create these vectors. Right? Let's create our co-occurrence matrix. So now we have some more meaning behind it, right? Here's another example, Mayan hands, right? But what do you think are some issues with this? What might we not like about this co-occurrence matrix? And I'll give you some clues. What were some of the issues we didn't like before about a one-hot vector?
The context brings different meanings.
Sorry?
So let's say like on hands and hands on might have a different meaning if we could.
Right, yeah, so that's one issue that maybe order
Yeah.
might matter. Yeah, that's definitely one issue. We're not gonna handle that right now. I might talk about something later about how to deal with that. Let's think back to some of the issues that we didn't like before about one-hot vectors, yeah?
Maybe we don't know when we're gonna see these words together.
Mhm.
When in the
Yeah, so one thing that, so the way we'll actually go about learning this vector, this matrix, co-occurrence matrix, is we'll actually read large amounts of text. So you might read all of English Wikipedia. So that's how we're gonna compute these co-occurrence matrix, just to make it feasible. Right now, I put a small snippet, right? I wasn't gonna have us go through all of English Wikipedia. That's what computers are really good at. But what do we think are some issues with this that we had before with one-hot vectors?
Very sparse.
Yeah, it's going to be sparse, right? And to anyone know what Becca means when she says that this is going to be very sparse? Any ideas?
Would you explain?
Yeah, so here, so what, if we just look at this co-occurrence matrix, what's the most common value in our table? 0, exactly. It's just not a lot of information. The most values will be 0, right? And what else is an issue that we had before? How long are these vectors going to be? They'll still be the same size of our vocabulary. So yes, we added some more information, but really we didn't add that much. And we still have sparsity, and we still have a very large matrix that won't necessarily fit into memory. Right? I think the question, what was your name?
Kim.
Kim, right? And Kim mentioned about, so here I asked is meaning captured. Kim made a specific point of, here we're making assumption, a naive assumption about content, about word order, not matter. So the solution that we're going to take here is we're going to just make the vectors from the co-occurrence matrix smaller. And so how many people here have taken linear algebra? A few, yeah. So this is my pitch for why you should take linear algebra, and specifically the computational linear algebra approach here. So there's this method called singular value decomposition. And what it will do is we'll basically take a very large matrix and densify it, right? So it'll make it much smaller, much more compact in a way that retains the most important information from your matrix. So we're not going to necessarily go into those details of how does singular value decomposition work, but I think this should be a good pitch for why you should take linear algebra. Then you'll really cover how and why this works. So that's one method that's commonly done. Another more recent method is called word-to-vec. Right? And here what we're going to be doing is we're going to be using a neural network to learn this. So we're going to feed as input our text. So we're going to give the neural network a single word, and it's going to have to predict what the context is. And this is called skipgram. Right? We're not going to necessarily go into all those details, but what we end up getting are much more compact representations. So that's really the way that we're going to create these representations that computers can understand. And there's been a lot of work showing how word embeddings preserve meaning, verb tense, in country and capital. And I've done a lot of work on understanding word embeddings, coming up with better methods for word embeddings. So Kim, you mentioned the issue of order sensitive. So I had some work from a while back that basically tried to look at that specific issue. Cool. So that is word embeddings. For the sake of time, we're going to basically skip sentence encoders and multi-layer perceptrons, and we're just going to basically use those as a black box. Right? That's how we're going to view it from here on out. Right? So that is natural language inference, as well as the typical modeling approach for natural language inference. And we specifically focused on basically the issue of word embeddings, or how do we represent words in a way that computers understand them. So now I want to talk about deficiencies in existing tests for natural language inference, right? So remember, here's our example. Millie ran across the field, would likely be entailed by the sentence, the mascot moved. Right? The first issue of this is that doesn't necessarily help us understand the limits or the reasoning capabilities or why systems are failing, right? That just gives us some sense of, yes, our model can understand whether two sentences are describing similar events, right? And here we can see that numbers, the accuracy of this performance of this type of on this task has improved, but it doesn't really help us understand what's going on under the hood, why our model's failing, and things like that. So this brings us to the diverse natural language inference collection, or DNC in short. Right? And that's what we're going to talk about a bit right now. This is based on work from 2018. One thing I want to note is, so Aparajita Halter was a visiting undergrad at Hopkins at the time. Now she's a PhD student in the UK. And part of this work I helped supervise as part of her undergraduate thesis. So I want to point out Edward who was a sophomore, I don't remember one or two at the time, who was a linguistics major and had taken one CS class. And this is really a lot of work that is really accessible for undergrads at all levels. He actually went on to work as like a rotational programmer at Microsoft AI, and now is a researcher at Microsoft doing lots of great work. Right, so this is what the DNC is. It's a large-scale collection of diverse natural language inference problems. And what it is, the way we go about creating it is we convert reasoning tests from existing data sets into NLI. Right, so here are some examples. Let's look at the first example, focusing on puns. Right, so we see the premise here is Kim heard masks have no face value. Right, and that entailed by Kim heard a pun. What do you think? Yes or no? Yeah, that would be right. So really the thinking here goes is that if we create these types of examples, right, they might indicate that our models are performing some aspect, something related to maybe identifying puns or identifying humor and things like that. Right, so this is the initial release of the DNC from 2018, where we have lots of different phenomena, different types of reasoning capabilities that are important and gendered in AFRA. So this is basically linking co-reference, he, she with the item, with what it refers to in text. And these, when we released it, was pretty large, 500,000 examples and growing. We'll talk about some of the extensions. So this is work that we open sourced, made it publicly available. And it's something I really try to do in a lot of my work is really let's push work to make it accessible to others, make our code accessible and data as well, because I think ultimately research is not just about doing interesting stuff, but really having a broader conversation, give and take with the research community. Here are some extensions that I've worked on and released afterwards as well. So I briefly want to talk about this method I refer to as recasting. So here we define it as leverage existing annotations to create an NLI data sets that probe different types of reasoning. So we're going to take existing resources and we're going to come up with lots of methods to basically create focused evaluation data sets that probe different types of reasoning. Right, so here we can see some more examples. Here's one on event factuality. So this is factuality is a phenomenon in linguistics on whether an event described in text actually happened or not according to the speaker or author, right? So if I said I hoped to get an A on my test, right, that doesn't necessarily mean that me getting an A on the test happened, right? So here we have some examples. So we have my newborn daughter helped me a lot, right? That would entail the helping happened. So part of this was really a call to the community, or for people that are focused on specific phenomena in linguistics and natural language processing. The goal is for them to convert their data into NLI and to be included in future DNC releases. And here we have work from a group in India that created a similar data set in Hindi. And here it's actually someone who I worked with when I was at Bloomberg, and he also was like an adjunct faculty in India. And really something that I like about this is it really just shows how the research community has taken this idea and sort of run with it. The second aspect of this, which I think really is the important part, is let's use these examples to find the fail cases of NLP systems. And that's really what we're going to talk about right now, is using these sort of data sets to see where and why some systems fail. Cool. If anyone has any questions, now is like a good break. Wait for me to pause. That's okay. We can go on. So I'm going to focus on machine translation, right? So what machine translation is this task of given text in one language, right? Give me the same text in another language, right? So I'm sure many of you used Google Translate, but there are lots of applications out there. There's Microsoft, there's Weibo, lots of examples out there. And the reason why I focused here is there's this great quote from Philip Cohen, who wrote the book on machine translation. Basically says, researchers in deep learning often do not hesitate to claim that intermediate states in neural translation models encode semantics or meaning. Right? And what he's basically saying is that there's a lot of work in machine translation, and you see that really, if you use Google Translate, you'll see it works pretty well. There's a lot of hype around this, right? Where people basically say that because I have a system that translates language so well, it understands language, right? So that's what his quote is saying. Basically, this ding against researchers in machine translation. So that's sort of why we started with this, because our goal here is really, let's use the DNC, let's use this format of natural language inference to see the limits of machine translation, right? To see really where and why, what does it do well at and what does it not actually do well at. So we're going to focus on two tasks. One is anaphora resolution, another is paraphrastic inference. Say we have this sentence that we're translating in English. Right? The father fed the child because she was hungry. Right? Say I ask you to translate this into Spanish. Right? How should we translate the word child? Niña, how come?
The sheep.
Yeah, does everyone agree with that one? Yeah, a lot of Spanish speakers here. Cool. Yeah, exactly, because she refers to the child. Right? And here are some examples of Google Translate actually getting it right. This was a recent one where I did get it right, but in the past I have examples where I failed. The second phenomena or limit reasoning capability we're going to look at is paraphrastic inference, right? So here, let's look at this example. The father fed the whippersnapper because she was hungry. Right? Does anyone know what a whippersnapper is? Fish, yeah, maybe. I see a lot of head nods, a lot of Gen Zers here. So let's say, right, exactly, if you aren't reading books from the 20s to 60s, you obviously know what the whippersnapper is, but imagine you have access to maybe a source. You know that whippersnapper here could be a synonym for a child, right? So you may want your system to be able to make this connection when when seeing something that's never, a word that's never seen in training, or it's never doesn't know how to translate, right? So that's why we focus on those two phenomena. So what I want to talk about here really is the mechanics of how do we use the natural language inference data sets that we create to test the limits of a machine translation system. So there are three steps. The first is we train our machine translation system. And you can view these sort of as two black boxes, where what we do is we give our sentence in English, right? Like the father fed the child because she was hungry, to the green. And then the yellow part has to take whatever was learned by the green and translate it into Spanish. Does that make sense? Next, what we're going to do is we're going to take the encoder part, so the black box that basically takes in and comes up with a representation of our text, right? So we're going to pass in our NLI examples into that part and extract representations. Then we're going to train a classifier to make an entailed or not entailed prediction based upon those extracted representations, right? And the thinking goes that if the system is capturing paraphrastic inference, or the system is capturing anaphora resolution, which we want our machine translation systems doing, right? We want our translation system to identify the leader of China, not as how it did, right? So the thinking then goes is that if our system really captures this, then the representations that it's learned really should be useful to make this classification. And for those that are in there, we can actually skip some of these details. This is what was the specific model at the time. We looked at systems that went from English to all of these different languages. Okay? So we have Arabic, we have Spanish, we have Chinese, we have German. Cool. So here we can see basically our results. How well did this classifier that took features from a machine translation system actually do on an entailment that was focused on paraphrastic inference? So let's look at these bars. And so here on the right, let's start with the right. This 80 represents a system that was trained fully just on this task, so independent of machine translation. So this 80 basically gives us the upper limit of how well we could expect any model to do. Here we can see the light blue, the 57.5, is basically whether in this data set you always predicted entailed or not entailed. So this is a stronger baseline than 50-50. Okay. What you can see here in these different colors basically are all lower than this 57. So what that means, that might indicate that yes, this machine translation system works well, but it might not actually capture, it might fail on paraphrastic inference. And something that's interesting to note is we see differences between when the system was trained to translate into different languages is I think a pretty interesting finding right there. I've done lots of work looking at models. Yeah,
Quick question.
yeah, of course.
I was trying to understand if you go back one more slide. One more on the model.
That one,
So,
yeah.
yeah, so you're training this MMT model, an MMT model, and then test it on NLI.
Yeah.
So you hope that the neural model, based on the parallel data it learned, is gonna be able to do NLI tasks.
Well, so we train a different class. So when I say NMT, for everyone, that means just neural machine translation. Just think of it as a deep learning, fancy state-of-the-art machine translation system. So the answer to your question is not really, because what we're doing is we're taking a different classifier that's not trained for machine translation, just for NLI, but with the features we use come from the machine translation system. Because what we're doing, we're basically saying, machine translation system, you've learned some internal representation, like these word vectors that we spoke about earlier, for these examples, for any text I give you. So we're going to give it the text from our NLI examples and ask it to ask a new classifier to make predictions from those. So in our DNC data set, we have a train, a dev, and a test split as well. Does that
Okay,
answer
so you're
your
just
question?
using the representation.
Exactly.
So then what are you comparing against with this representation and not with?
Yeah, so what we compare it against basically is this on the right here, which is a model where the encoder wasn't frozen, where the encoder was specifically trained for this task as well. Make sense? Awesome. Cool. And since I've been here at Barnard, this is work that I've really continued pushing forward. So this is work that presented at the Nlp 2020. Siddharth was a junior PhD student at Rochester at the time. And Yash was a master's student at Hopkins that I co-supervised. And then here at Columbia, I've been working with Miranda and some of her PhD students to look at figurative language. So we wanted to look at how well do NLP systems capture figurative language as well. And I've done work really surveying this entire natural language inference, also referred to as textual entailment, as an NLP evaluation as well. So that really concludes the first half of this talk, really using natural language inference to evaluate NLP systems. And I have other work with some students here at Barnard and Columbia, where we're going beyond this natural language inference setup. I'm happy to talk about that after. I just left it out to the scope of this talk. Cool. So now I want to transition to the second aspect of this talk in a lot of my work, which is really the applications of natural language processing beyond consumer products. And here we're going to refer to this as computational text analysis. You might have heard text is data, very similar terms, but here we're going to use computational text analysis. Right? And we're going to look at these three aspects. We're going to first take a broader view of NLP, where I think I'll pontificate a little bit, and we'll look at some examples of using NLP methods for text analysis. And so let's first start with what is NLP, right? So remember, we started this talk by saying NLP is a subfield of AI that's focused on building human language technology, right? So you can maybe just refer to this as HLT. But there's a much broader scope of natural language processing. I like to view it sort of like this, that we have these two different poles. One on the right is computational linguistics. And here in computational linguistics, we're not necessarily interested, folks aren't necessarily interested in building real world tools, but rather really are interested in studying language. There are questions, they're scientific law, are questions of language. And what they want to do is, instead of coming up with 100 examples, analyzing them like linguists often do, they want to use the methods from NLP, right, to study language on a larger scale. On the other side, we have machine learning researchers, right? Where machine learning, the goal is I want to build a system, doesn't necessarily need to be a human language technology system, but I want to build a system or come up with an algorithm that can learn from data. They can find patterns in data. And for these machine learning researchers, language isn't necessarily the goal, but maybe is the sandbox on showing that their machine learning algorithms are better than others, right? Or that they really can develop a system to find patterns from data. Right? That is the goal of machine learning, often referred to as algorithmic contribution. And the goal of computational linguistics is to understand humans and language. Then I think we have another spectrum. One is maybe AI, artificial intelligence. Another one I refer to as CTA, right? So oftentimes I'll say the goal of AI, I think a little bit of a joke that I don't really know what this is, science fiction, but in truth, I believe that there are folks in philosophy who really are primed to ask these types of questions, like John Morrison here at Barnard, who teaches a class on neural networks from the philosophy department. For CTA, right, often referred to as text as data, right? And this, I think, is my view of natural language processing that goes beyond human language technology. And a lot of the work I've been focused on more recently is this computational text analysis, where what we want to do is we want to broaden the types of questions that researchers in other fields, like economics, psychology, nursing, political science, can ask and answer by analyzing large amounts of text and moving beyond maybe traditional surveys or other methods. So I first want to define, what do I mean by computational text analysis? Right? So I want to take this quote from Jeanette Wing, who was the director of the Data Science Institute and now is executive vice president of research at Columbia, where she defines data science. I'm sure many of us have heard data science. It's a pretty popular buzzword nowadays for to class in data science. But so she defines data science as the study of extracting value from data. And I want to use this as a springboard for what I refer to as computational text analysis. So here I say CTA, computational text analysis, is I think the practice, we're not necessarily study this, but it's practice of extracting value from large scale textual data. And that's sort of how I go about defining computational text analysis, building off of a lot of work from Jeanette Wing. So now we're going to focus on 3 projects. I think we have enough time to talk briefly about all 3. First is focusing on social media for tobacco regulatory intelligence. And then other projects will focus on a bit as well. One focused on discovering the impacts of COVID-19 had on birthing families. So these are families that had new babies, new children during COVID-19, and as well as identifying and characterizing math-related anxiety on social media. So we'll first talk about social media for tobacco regulatory intelligence. This is work done in collaboration with others at Hopkins, the FDA, and University of California, San Diego. And what really we're trying to do here is we're trying to discover new e-cigarette tobacco products that maybe regulators don't know about, but yet are popular on the market and people are talking about online. So the way we go about this basically is we start with a seed list of terms. Right? So does anyone recognize any of these terms? I see head nods, I see some. Yeah, I see more yes from the Gen Z crowd. Cool. So these are some terms, right? These are popular seed lists. And what we're basically doing is we're mining social media platforms, right? So does anyone know what platforms these are? You know, top one?
Reddit.
Yeah, the bottom one.
Twitter.
Yeah, exactly. So what we're doing is we're mining these to basically find what are similar terms what are terms that people use in similar ways to these that regulators don't know about, right? And the method that really we use a lot here, what do you think the method we're going to use maybe that worked the best here is? Any ideas from earlier in the? Yeah, so word embeddings is something that we actually used a lot here. So what we did was we basically collected a lot of data from Reddit that focused about e-cigarettes. We collected a lot of data from Twitter that focused on e-cigarettes, and we learned representations for all of these terms. And basically using the representations that we learned from our seed lists, we can use methods from linear algebra, like cosine similarity, other similarity metrics to figure out what are other similar terms. And that's exactly sort of what we did over here. Right? So what we did now was after mining Reddit, mining Twitter, we could rank a list of terms that regulators that weren't on our seed list, regulators didn't know about, but yet were used a lot online, right? So here, has anyone heard of ZIP? So ZIP was one of the examples that our collaborators or don't subject matter experts actually didn't know about. We have a whole list as well. And what we did for part of this was we created an annotation guideline. It's pretty long. And we hired a team of about 15 Barnard Columbia students to annotate the discovered terms based upon our annotation guideline. And we had a pretty successful hit rate of terms that we discovered that actually were new e-cigarette terms, products, retailers, manufacturers that maybe regulators didn't know about. Cool. So I want to talk about the second project called Discovering Changes in Birthing Narratives During COVID-19. And this is work done with 2 Barnard undergraduates, Daphne Spira and Noreen Mayat, as well as in collaborations with Caitlin Dresbach and School of Nursing and the Data Science Institute. And here, what we really wanted to look at was there's a large community online, specifically on Reddit, of birthing parents that describe the experience that they had giving birth. Right? So they can describe what it was like in the hospital, maybe they describe home births and things like that. And what we basically did was we collected, what the students did together, we collected about in the thousands of these types of narratives. And we used lots of NLP methods to really analyze what was going on. And one of the methods in particular that we'll talk about for now was topic modeling. And what we do in topic modeling is we're given a large collection of text, right? So here we have lots of Reddit posts describing birthing narratives. And what the goal is, we want to find groups of similar terms that represent topics. What we can do from that is we can then plot the frequency or the rate of how prevalent were these topics throughout our corpus. And with that, what the students did, we basically plotted that, but we basically looked at everything up until COVID-19, right? So that's what the red line is. So here we can see this is the topic about induction, right? So these are terms like cervix, hours, induction, pitocin, Foley, all induction related terms. And what we basically did was we plotted, so the black represents the actual, right? And we basically, the blue, light blue represents a model that we fit to this data. So we see, we fit our model basically along this. And at the start of COVID-19, so around March 2020, we basically had our model make a prediction. We said, based upon everything we've seen so far, how would we expect this prevalence to continue in the future? Does that make sense? And that's what we see as this blue over here. Okay? And if we look at what actually happened in reality, what did we see in the text, the blue over here, we saw a significant increase of the discussions about induction, right? And this aligned a lot with actually what happened in the field. And it's interesting that a lot of this work, we can see that the real effects that clinical decisions can make on the experience of birthing parents, on the experience of patients, right? Another topic that we looked at was family. So here again, we fit the model of family, right? And we predicted from COVID-19. And we can see here a significant drop, right, in black below. So we can see here that family, presence of people like mothers, husbands, families, siblings, appeared a lot less. And this corresponds, we theorize that this basically corresponds pretty well with how hospitals had restrictions and limitations of who could be there during birth and things like that. Yeah.
About the induction, how is this related to COVID?
Yeah, so what it is, so basically the topic of induction isn't related to COVID. But what we did was we trained a model on the prevalence of this topic. So you can see that x-axis, I should explain this first. The x-axis here represents the dates, right? So this is a monthly, so 2020, 2011, 2013, I believe these are monthly points. And here basically represents what was that average probability of this topic being discussed in across our corpus, across all of our documents. So that's here. So what we did was we fit a model that basically looks at what is that prediction, what was the average topic probability from the beginning of our corpus in 2011 up until right before COVID hit. Then what we did is we did a time series projection to see, given everything in the past, if we would continue in the future, just like how the past was, how would we expect this topic probability to be going forward, right? And here, basically, we compared the prediction post-COVID with the actuality of the COVID time period, basically. Does that answer your question?
No, I just want to get like a layman's understanding as like you're doing COVID, it seems like the induction topic seems to be steady, or is it?
Oh, it seemed to rise. So that's the black.
Okay,
The black represents the actuality, what we saw in our data.
so why is how is induction related?
Yeah, so our hypothesis.
Getting induction?
Yeah, so our hypothesis is that, and there's some work in like some medical and nursing literature about this as well, that basically people were electing to plan their delivery because they wanted to get COVID tested before and things like that. So there's a lot of literature in the nursing community about that, basically.
Thank you.
Awesome. Any other questions on this? So I'm going to highlight one other project. This is in collaboration with Isha, Olivia, and Jalisha. Jalisha from the psychology department. One thing I just wanted to Olivia was an English major at Columbia, at Barnard, and took a few computer science classes, including my computational text analysis class. And in this project, we were focused on looking at really seeing how is test anxiety described online. Right? So Jalisha is the expert on test anxiety in general, not test anxiety. And here we wanted to see, first off, we asked the question, do people talk about test anxiety online? We showed yes. And we also wanted to sort of characterize how did this test anxiety, how is it different across different online communities? So I don't know if you're familiar with Reddit, but Reddit is composed of what's referred to as subreddits. So these are communities that the discussions are centered around specific topics. Right? And here what we did is we categorized lots of different subreddits as being academic, medical, advice, or sexual, a few others as well. And what we basically did is we used statistical methods to see, in NLP methods, to see, are there terms that are indicative of different topics or of different Reddit communities? Right, and here you can see are some of the differences that we see. So we can see that if people online in their corpus were talking about like math anxiety, they often were looking maybe for advice rather than maybe venting and things like that. In the sexual category, you can see a lot of terms that maybe are indicative of ways that people describe maybe how do they deal with stress, anxiety. Lots of work, continue this project as well, where we're looking at maybe gender-based differences that we're able to infer using NLP methods as well. So sort of to summarize this portion of the talk, we looked at in my view of the natural language processing field. We looked at some examples of using some of these methods for e-cigarette discovery, for looking at test anxiety online, and seeing differences in birthing narratives before and after COVID. And this really fits into my larger research agenda of also looking at the limits of natural language processing systems. So I want to thank you all for your great questions, for being awesome and lively audience. And I want to thank a lot of my collaborators on all of this work as well. And I want to note that a lot of my collaborators really are span lots of institutions, lots of different types of places. And this is really a network that I have been leveraging here to help Barnard students go, what do they do after they graduate? If they want to go into academia, they're great resources of people who I think would make great advisors and feel I've sent students to, as well as companies as well. We have lots of connections and where really students have started to work as well. So with that, thank you. I'm happy to. We got it under time, right?
Yeah, you're good. Second breath. Any questions on the Zoom? You can unmute and speak. You can raise hand. You can put stuff in the chat.
I'm gonna stop sharing.
Okay.
You can also DM me if you don't want other people to know. Yeah, Mark?
I think it was slide maybe 107, where you were
That's impressive.
where you were comparing the MNP to the paper from White in 2017. I think.
Yeah.
I didn't quite get that what MNP was. That was some sort of baseline benchmark.
Yeah, let me share my screen again. I can go to Zoom, Zoom, share screen. Should full screen it? Let's full screen. I'm not going to full screen, but I think it's fine. So you're saying here over here?
Yeah, what was that one?
Yeah, so this majority baseline, slower job of explaining it. But what is, so this, remember, is a binary classification problem, right? We have two options. It's entailed or not entailed, right? So if what a random baseline, right? If I was just flipping coins, would be 50-50, right? But what a majority baseline is saying is that, so that assumes we have an even split in our data, right? That half of our examples were entailed, half are not entailed. In actuality, in the data that we used, we created 57.5% were not entailed, and 42.5. Yeah, 42.5. Yeah, still got it. Would be entailed. So this is just a stronger baseline compared to like a probabilistic 50-50 view. So, but what's we show here is that, like, so if we looked at just these numbers, 56, 55, we'd say, oh, look, it's better than chance. But in reality, because we use what's referred to as a majority class baseline, it actually isn't better than chance. Thank you. Oh, 107, you're right. Impressive.
More questions?
You have a question?
So just follow up on that. So basically this graph is showing that the representation we learned from machine translation is not useful.
Exactly, for this focus,
For this
natural language
particular
inference,
paraphrasing,
on
yeah,
paraphrastic
right.
opinions, exactly. And what really I think the takeaway is like, you can't necessarily make these claims that machine translation systems understand language. And I think this is sort of my one approach of looking at, can we see limits of NLP systems? Because at the end of the day, we can come up with lots of cool fail cases, right? You can put lots of examples through Google Translate and let's see where does it fail. But here, what I like about this work is it really tries to approach it from a more systematic way of let's focus specifically on paratrastic inference. Let's specifically focus on something like figurative language, right? Let's focus specifically something on like temporal reasoning, like can a system understand which events happen before other events or how long events take place?
Yeah, so there are a lot of people specifically trying to understand, for example, numeric, basically how numbers work.
Yeah.
Representation, how different specific articles work or something else.
Yeah.
But this particular just makes me wonder. So it's a very rhetorical question, right? If the machine translation systems are doing well in general,
Yeah.
do we actually need the machine translation system to know these specific, very archaic characteristics of these kind of NLR questions?
Yeah, I think that's a perfectly valid question, but this is why I'm motivated like this, is I think if we want to improve these systems, right, they're not foolproof, they're not 100% perfect, and we see when they fail, you can have diplomatic issues, right? When it fails and maybe you're translating a contract, or maybe an analyst is looking at it, using a tool that maybe extracts some information from a contract and mixes things up. That's why, like what I find really exciting about this type of work is that despite these successes, right, natural language processing is no longer something just reserved for the academic setting, but despite these successes, and I would probably argue that forever, even as we improve these systems, there's always going to be failures, right? And that there's always going to be a need to understand these failures.
So is it possible to make this an LI task as a pre-training task or as a extra co-training task?
Yeah, so there's lots of people that have done that basically have taken this. So with a question, what was your name?
Oh, I'm Joe from computer science. We never met in person.
Oh, awesome. So I think the question is asking for like everyone else. So if we look back at this let's look at this example from our, let's go back in a quick second. I just want to put that figure of the whole. In a quick second. Sorry. No, we're almost there. Almost there. Yeah, this one, right? Cool. So that's what she's asking, right? Is so here, this is our, let's ignore everything over here. Let's ignore this, just focus here. So this is a machine translation system, right? Does anyone, let's think of a step bigger back. Does anyone have any idea how do we train things like Google Translate? Yeah?
They use Google Books. Like,
So Google Books, yeah, so we use books, we use collection of text, right? But what type of collection of text do you think we're going to use? We're going to give to a machine translation system. What's special about maybe the text we want to give it? To give you a clue? 2 clues. Think Bible, but also think appliance manuals. Yeah, that's a good question. What's similar between appliance manuals and the Bible? Yeah, Paratrastic?
Instruction, like people look to them, like people reference them regularly.
Right, so a lot of people reference them. So what do we think would be a consequence of a lot of people referencing them?
Already in a lot of
Yeah, they're in lots of languages, right? We have, if you look at your appliance manuals, your dishwasher manual. Like I said, I've gone through a dishwasher manual recently. Hope you don't have that need in college. But these, right? So we have what's referred to as parallel text. So what we do to train these systems is we basically give it like a Bible in English and a Bible in Spanish. Or we give it the, I don't know, Maytag, dishwashers, English and German, right? And we have it learn these patterns on its own. That's how we train a lot of machine translation systems. So I don't know if it was a few years ago, there was an issue when Google Translate, whatever people were putting in, came out sounding pretty biblical. That's not had to do with any issue related to this. So the question that she's asking is, what happens is let's take this architecture, well, let's first train it. So here we're first training machine translation. We're using that to extract features for NLI. She's asking is, what if we first train our system for NLI and basically swap this out for NLI and then put back this encoder to help with translation? And the answer is like people have done that for lots of different tasks and it seems to help. The nice thing about a lot of these deep learning methods that we didn't cover at all is that there's something called multitask learning, where you're able to build a system that can actually perform lots of different tasks at once and learn similarities between those as well. Yeah, I can answer your question first.
This is like thinking about the limits of all of this as well. But when I think about survey data, there's like a lot of thought given towards like the sample size, who makes up the population, and all of that. All of those sampling methods are pretty rigorous.
Yeah.
And like a lot of effort goes into trying to represent a lot of different groups, especially like I know historically underrepresented ones.
Yeah.
And so I wanted to ask about how y'all incorporate the fact that you can't always you can't really tell those things with social media, and also the posts themselves are self-selected.
Yeah.
And so like how do you guys like account for that?
Yeah,
Like,
so for the first question, that there are actually a lot of methods out there to infer. It doesn't work all the best. Well, sometimes works pretty decently enough to infer some demographics. But the reason why I bring this up is because I just want to ask, basically in a lot of this type of work, it's computational text analysis of work, a lot of really the hard part and a lot of the really majority of the time spent isn't on a lot of the methods. It's really not, sometimes we have to develop new methods, and in that work, that's the contribution. But really in a lot of this work, the majority of the bulk of the time is spent on data collection and data curation as well. So like if you read a lot of these research papers, that maybe will have like 3 sentences about how the data was collected and curated and cleaned. But that's really exactly where a lot of the work goes in. So there are lots of like best practices that are often used for that to ensure good sample size, good quality size. And that's, I think, also a really exciting open question as well. Is like, can we maybe come up with automated methods to help with that? Yeah.
Would you please show a slide 99, I think?
99, this is a engaged crowd. Yeah, this one.
Yes, thank you. So your Bible example just made me think, I don't know if it makes sense or not, but so for Bible, I'm assuming that a lot of the translations are gonna be like word by word.
Yeah.
But I was thinking like, for example, if you use like popular literature books.
Yeah.
In those cases, most of the translations are based on the context of
Yeah.
that particular language. And that can help you with that context.
Yeah.
So it's
Yeah,
like-
so there are lots of different machine translation approaches. Some are word-to-word alignments, some are phrase-based alignments, some are whole document alignments. Actually, Sus Miranda, who's on the call, is I say like the expert in like creative language and sort of, and she has some students that really are focused on this issue, like how do we generate creative language? How do we build systems to create generative language or learn from creative language like literature and things like that. And that's, I think, also an exciting aspect and a big open problem is how do we take methods that work in maybe newswire, news text, Wikipedia, online sources, and apply those methods to creative texts where a lot of those assumptions break down, right? Like word order is something that's really important in creative text. It might not matter as so much if it's just like a report written for like just literally straight for information and things like that. I think these are all great questions. So I feel like this is around of time.
Yeah, we should probably wrap up. Thank you so much. Thank you for coming. Thank you for your questions. Thank you for those of you on Zoom. And for those of you in person, feel free to grab and go some fruit on your way out. And enjoy your day. And thanks again for us.
Thank you.